nanohub.org. Online simulation and more for nanotechnology.
My pleasure to introduce Aaron Franklin, who is a graduate of Purdue, and not only that, but the Burke Center. I think he was here when we opened this place. He graduated in 2008 with his PhD from electrical engineering, and David James was his main advisor. I was his co-advisor. And since then, he's been at IBM. He's now a research staff member, and he has achieved many things. When he was here, he was a National Science Foundation Fellow. Since he's left, kind of the way I describe his career trajectory is that as the research community in nanocarbon devices has hopped from one bandwagon to the other one, Aaron kind of stayed on one and moved his way up, and now he's, I think, pretty much driving the train for carbon nanotubes, which makes sense because his nickname when he was here was the A-Train. And then there's something that's not in his bio, but I mentioned to him before. I think that he is the record-setting student of the Burke Center for accumulating the most lab charges in 1 year. Okay, and I think Steve Hudson might be second. But I remember 1 year when he racked up $75,000 in user fees at the Burke Center. One student. And when I say that Dave James was his advisor and I was his co-advisor, if you did the financials on it, it wouldn't be that way. So
should I add that to my CV?
Yeah, you should add that. He's won a lot of stuff. He's doing some really neat things. You should read his recent papers out of IBM where he talks, in almost philosophical terms about devices with carbon nanotubes and also some other technologies like graphene. But what it all means and what really might happen with carbon nanotubes in practice and carbon nanotube devices. So hopefully he's going to talk about that today and teach us a little bit. So it's my pleasure to introduce Aaron.
Thank you so much, Tim. So it's always fun coming back because of the memories I have being here, obviously, but there are a few things that you forget in time. And one of them was, as my wife and I were driving over the Wabash this morning, was remembering it being a lot bigger than it is. But when you live by the Hudson, it makes the Wabash look like a creek in comparison. So it's really fun, though, to see how everything's growing and how well people are still doing here and exciting changes being made. So it's fun coming back for the nostalgic effect and also for the opportunity to show you some of the things that I think are exciting that we're doing at IBM. You're going to notice something different about my approach. As I've been told from a few people, I'm very honest. And it's intentional, which means while it may seem, occasionally like I will hype something, I will be very honest about what the shortcomings are. Because the fact is, as Tim mentioned in his introduction of me, which I'm grateful for, I still work on carbon nanotubes, and this field is full of a lot of misconception about why people should or should not still be working on it, whether it's still alive or died, and we're trying to resurrect it. And I want to make sure, if nothing else, to correct that for those of you who've taken the chance to come this morning. And with that, also provide sort of a broader picture of nanoelectronics, where the field is going, and where, with maybe only a little authority, I can tell you where IBM stands on that whole picture. Okay? So here's the outline, and I pretty much mentioned that already, so we'll jump right in. I'll give you a little history for those of you not overly familiar with IBM. You have two members of the faculty here who are from IBM, the very lab I'm from, Jorg Appenzeller and Zhihong Chen. Zhihong, who I worked with when I first went to IBM after leaving Purdue almost 5 years ago. And this is a picture of the company if you're not overly familiar with it. There are 430,000 plus employees, minus maybe 6,000 in the last month or so. But those luckily did not come from research, and this shows you how small IBM Research is compared to this mammoth company. And this is a fun thing to point out because if you really knew what IBM's business model is today, you would realize, well, it's kind of a business services company. So what is IBM Research doing with that? And we like to say we are the face of IBM. IBM loves the accolades that the research community has brought in, and because of that, they can sell things like, complete solutions for your email and servers, because if we can do carbon nanotubes, of course we can fix your email software solutions, right? And we kind of have prided ourselves of being able to maintain that over the many, many years and the many, many people who've done amazing stuff there. But it is a small fraction of a very large company. The research disciplines within IBM are shown here very broadly. While the Watson Lab in Yorktown Heights is the headquarters for research, there are a variety of labs throughout the world. They're not necessarily split perfectly by discipline. There are some crossovers between those labs. Zurich and Almaden and Watson have the most crossover. My area is predominantly electrical engineering, but just like the Burke Center, we have a great deal of multidisciplinary researchers and a lot of creative collaboration that comes out of having that type of an environment. For semiconductor research, we have a bit of sort of a pipeline in place, and communication happens at different levels to make this work. But the idea is we have core exploratory research at Yorktown, Watson, Almaden, Zurich. Like I said, there's a lot of crossover there. And that, hopefully, whatever technology is being worked on there will push its way up towards Albany, where there's an advanced R&D center, which is moving now towards 450 millimeter. It's a great facility with a consortium of different companies that contribute to it. And finally, if something gets through the line there, they'll move it to Fishkill, New York, where we have an actual fab to push product out. So it's nice to have that type of pipeline in place, even when you're looking at an exploratory R&D level, so that you can keep in mind what the technical challenges are and how they need to be addressed in the long run with what you work on. So the transistor industry in general, and where most of my research focus is, I like to give a background using Moore's Law, as you'll see in a minute, but I want to try to re-educate how people look at Moore's Law. So this is what I mean. When you look at where things have gone with electronics, we have started to step away from caring just about how fast our processors are, how much memory there is, and all of these core technical components. And we care more about functionality. We want to know what can it do once it's in the hands of the user. And that's created a really interesting split on what we expect from transistors. Because for years, with respect to Moore's Law, we saw a very consistent reason for increasing the number of transistors because we wanted to increase computing performance, make them run faster, etc. All of these things were very straightforward. But there came a time about 8 years ago when we decided we cared more about application in some cases than we did about performance or transistor count. And we started seeing like the Atom processor from Intel delivered, which had a very low count but gave people what they wanted from their application. And this, I think, is a big part of what's missing when people look at where we're heading in 10 years, because it's not the same as it was when we thought about it 10 years before. And this is another way of looking at Moore's Law, and these are the two ways that most people see it, and this is where I want to create some of the misconception. Most people see it where they either see minimum feature size getting smaller or the number of transistors getting larger. And we all herald the magnificent postulation of Moore from 40, 50 years ago that suggested that this could be the case. And that's great. It's a really amazing engineering feat that we've managed this. But I think there's a couple of ways that make more sense to look at this. So one, this is a funny plot about this. This is more technical, makes more technical sense. This is the power, watts per centimeter squared, dissipated on a chip. This was made 10 plus years ago. It got a lot of attention though because people like showing how if we continued on the same trend of increasing the power on a computer chip, that it would hit, a rocket nozzle and the surface of the sun eventually. And of course, those things, it's not possible, and we can't move the heat away, good enough to allow that type of power on a chip. So what we had is a flattening, where we said we can't get any higher, around 100 watts per centimeter squared. We have to just flatline this and change other things about what's going on. And already this was a bit against the grain of the way that the classic scaling was supposed to work. We were supposed to be able to see a reduction of the amount of voltage it took to operate each transistor, and therefore, even though we maintained sort of the current, the performance, we could see some scaling of the power because of this. And this has not been how that part of Moore's law has worked. And this is what I sort of coined this power constrained scaling. Other people have talked about it this way. This is a simplified look at what some of the main dependencies of active power on a chip. We don't have time to talk about the other issues with power, but just looking at active power, you have a huge dependency on things like the operating voltage and, of course, the number of transistors. And we always want this to go up. And that's the way we look at Moore's law. No, we have to keep going up there because that's what matters. But if we don't scale this operating voltage in correspondence with the increase in number of transistors, then we're just juicing the power up more and more. And so this is what I think is one of the more accurate ways of looking at Moore's law. The blue is the traditional way, transistors on the left axis, number of transistors on a chip, but on the right axis, and in green here, is this supply voltage. And for really the years throughout the 80s and even before, there was very little scaling, if any scaling at all. It sat around 5 volts. And everyone was sort of okay with that. And pretty soon we thought, well, no, we need to do something about this. And I don't have all the data points in here, but it came down to 3.3 volts and sat there for a while. And eventually, there was no way to sustain that. And there was a bit of a scaling trend that occurred that almost flattened off in the early 2000s. And we've sat around a volt ever since then, where it really warrants a lower voltage on the transistors in order to reduce the power, but it's something that cannot be survived in terms of the cost and performance. That is an important part of Moore's law when we think about what we want devices to do in the next generation and how they're going to fit the applications with that. So here's my fun way of looking at this. When I talk about this road ahead for nanotube transistors, and I think in terms of the entire field, what does the road look like? And this is my sort of personal perspective. First, the rearview mirror is important. And so if you ever drive, you should pay a lot of attention to the rearview mirror. And if I'm driving on this road, what do I think is in the rearview mirror? I definitely think that classic Dennard scaling is in the rearview mirror. This is not disputable. We cannot scale transistors just by reducing or changing the dimensions and the doping by a certain constant that allows us to maintain all the other parameters. Doesn't work anymore. On the rearview mirror is also the standard bulk MOSFET. It is gone. No other technology generations will be delivered to you with a bulk silicon material. It is now going to have to require other type of thinning of that material or restructuring of it into fins, and that's now become a thing of the past. We also maybe are starting to see silicon in that rearview mirror. There's still technologies coming from it, but it's getting closer to the point where we really honestly cannot get a whole lot more out. And I think, unfortunately, that Gordon Moore needs to start going into the rearview mirror. Not because he hasn't done amazing things, but because we've relied too much upon strictly doing things based upon an old postulation, instead of considering what may give us the best next technology by application. And we're too bound in a lot of ways to what we've delivered for many years. So what's ahead? Well, we know already we're seeing the 3D devices, they call them, which are the FinFETs that Intel has a 22 nanometer out on, and others are working towards getting products on. We have a lot of people still working on 3.5s and all various forms of them. Whether or not they'll resolve the issues remains an unknown, but that's something that a lot of people have in their path, including Intel's predominant research is on 3.5s for replacing silicon. Tunneling transistors still receive a lot of attention because of the potentials for lowering the power, the big issue there, getting the operating voltage down. And I'll talk about carbon nanotubes today and where those fit in. And then there's this sort of gray misty area where I only put a couple pictures, but you could put dozens. And a lot of people have moved to mist. And why I put the mist over spintronics and neuromorphic computing is because no one really knows how we're going to use these things. They just sound real good. And these are non-von Neumann architectures. This is when I start moving away, in most cases. Some of them can kind of fit the model. It depends. But it moves me into a space where we're changing the entire paradigm of computing. And that could be a great thing, but it's also kind of an unknown thing. And we still have a lot of work to do with that. Okay, so let's build the perfect transistor. This is my way of making sure that whether you have a double E background or not, if you look at a transistor and said, I need it to work the way I'm used to them working, but in the best way possible, how would it look? And the first thing is you have this channel, the semiconducting channel that's going to carry the current. It needs to be very thin because I need to be able to put a gate on that to electrostatically control it as best possible. It needs to have ballistic transport. I can't be concerned about how carriers are going to interact in the channel. I just need to get them from one side to the other. Okay? No bulk effects. I don't want anything else that's happening around this guy to make a difference of what's happening in the channel itself. Gating, I need to be able to make a gate all around geometry so that I can get the best electrostatic control of this really small channel, because it has to be below 10 nanometers, which means I don't want to lose the ability to turn that channel off with that gate. The contacts also need to be very small, because making a small channel is meaningless if I can't make the contacts small as well. And the performance needs to be able to give me a lot of current for a very low operating voltage. All right? That's my perfect transistor. And it's hard for really anyone to argue with that, because for what we want out of a IV curve, this is the dream way to get it. So the question is, how do nanotubes measure up with respect to the perfect transistor? And the fact is, most of the things that make it a perfect transistor, a nanotube naturally lends itself to. It has all of the channel properties that we would dream about. It can give sub-10 nanometer gate length devices, which I'll talk about, and delivers high current density at a low operating voltage. The issues, one of them I'll address a bit near the end of the talk, is this gate-all-around geometry and things like variability and, I didn't circle it, but making small contacts. So the way that I've structured this talk is, and this gives you some more of those motivations in fancy picture format for why we like nanotubes, but the way I've structured this talk is to give you some of the motivation, but then try to spend the whole second half telling you where the problems are. Because the fact is, I can try to convince all of you why everyone should still be concerned about nanotubes and willing to consider them. But unless you know what the problems are and are willing to try to make a move to address them, there's no sense in motivating it anymore, because it'll never get fixed just by us working on it at IBM. Okay. So history of nanotube transistors, I like looking at it like this. This is getting a little old since I made this. It went to 2011, covered over a decade. I spent a few bleary-eyed hours staring at the computer looking at all the papers that had been published about carbon nanotube transistors. And this is the trend. Now, this is about transistors. The field itself would have had hundreds of thousands of papers, I think. But if you separate this trend by topic area, in other words, the papers that focused on nanotube transistors for digital applications, this is the number, sensors, thin film devices, RF, and optoelectronics. Of course, I was very disturbed by this sort of taper drop-off in the mid-late 2000s. And so I did one more search and found this out. Graphene comes in and starts taking over all of our nanotube research, okay, around the mid-2000s. And the other thing that I think is important, in spite of that, is that the work on digital application space, up to that time, the papers that were motivated for that space remained relatively consistent. And that's, I think, an encouraging fact of what we, and this is, worldwide research, the fact that there are research labs that are still receiving enough support to put some attention towards nanotube transistors for digital space applications. And we've seen that even at the scientific publication level. So the difference between nanotubes and graphene, now that I brought up a bit of a negative tone there, I think graphene has a lot of excellent things happening with it, and I think it's important to keep it separated from nanotubes for what it's good for. As most of you probably know, it does not have a band gap. And even though it's a great electronic transport material, has very interesting properties, it's more appropriate for something that doesn't have to turn off, like an RF application. Even then, it has a lot of heavy competition, but it has more potential there. And it's funny because no matter where I've gone and visited in the last few months, and I bring this up, and I always have someone say, oh yeah, but nanoribbons, right? Graphene nanoribbons. And you get a band gap, and then it's kind of like a nanotube. I said, yeah, that's great. A terrible nanotube. Why would I be motivated to go with a terrible nanotube when I could just use a nanotube, which gets rid of all of the edge states, doesn't have the same type of fluctuation issues, and but there's still interest because it's graphene, and that's okay. Maybe someone will figure something amazing out. So if I look at this is my last funny slide, and then I'll get into the core stuff. I like this analogy of a road trip and the are we there yet? So I just drove from New York to Indiana with my 3 small kids. And if you've ever taken a road trip with kids, you can have some appreciation for that. It's kind of, when I think about it related to research, it's kind of like the parents are the researchers and the kids are the funding agencies. We're doing this for them, right? I mean, when we told them we were taking the trip, it was because we told them how amazing it was going to be. They were going to have so much fun. It was going to be worth every second of the trip. And mostly we did that by telling them how awesome the place we were going was, right? Like this CNT paradise. We talked it up to no end and we got them so excited. They were willing to do anything to come along for the ride. So we got them in the van and we started on the road. And you know what? I don't even know if we left New York before they were like, are we there yet? When are we going to get there? And then as we're making good progress, graphene land shows up on the side of the road. Just when we were really starting to make sure that we were making the right progress towards our end destination, the kids started saying, can we stop, please, 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 please? It's nearby. We're tired. We've been along this road for a long time and we need something new, right? Unfortunately, a lot of people got out. But what they figured out is that there was a lot of bad things in graphene land. Long lines, overcrowding. And even though the first few rides were fun, it was hot outside and they just started thinking, gosh, what are we doing here? And some of us got out and decided to walk. Now, whether or not we'll ever make it, who knows? But, and this is, I know, a little bit of a slapstick way of looking at it. But the problem is, when you have a good material as a very promising properties for electronics, we have to question how much time it should take to deliver the end goal. And in this case, we never got there with nanotubes. We still haven't gotten there. But should we still be trying? Is the question that people are not asking. And they should be asking it. Because instead they're jumping over to new materials. And I keep saying, but why did you get out? What made you get out of the van? And this is the kind of conversation that I think needs to be had more. Okay, so how nanotubes work? I mean, for many of you guys come in, we've got a lot of mechanical engineers here, so you're going to get misty-eyed, or kind of, glazing over on me as I go through this talk. So this is a little bit of a double E's look at solid-state physics for you that maybe it'll be insightful. About how a transistor works. And it's usually meant to talk to people who know how a MOSFET works and compare a nanotube. But if you look at the energy bands, this is a band gap, no carriers could be there. Here's electrons, this is a silicon MOSFET, and this is the IV curves in the subthreshold off state. When it's turned off, there's a huge thermal barrier. I can't get carriers to get over there. No matter what the thermal excitement is of them, they can't make it over. If I put a bias on this electrostatic gate here and I move these bands down, it lowers that barrier and carriers get over. But see how they bounce down to the edge of the band there? They're scattering. They have a certain mobility, a property of this semiconductor that tells me how well they transport from one side to the other. So here's the difference with a nanotube transistor. And this is a generalization, but it gives you some feel. Even though the curves look the same, there's different stuff happening here. This is how my band structures will look. And instead of having sort of a natural doped semiconductor junction for my contacts, I have metal to semiconductor contacts, which is known as a Schottky contact. And that creates its own type of barriers that I'll show on the next part. But for the off state, it's kind of similar. There's a thermal barrier. Carriers can't get through, and so the device is turned off. But in the on state, I have, in most cases, a small or, depending on the contact metal, substantial Schottky barrier, where carriers either need to be able to get over or to tunnel straight through. And the unique thing is that while that's new, what's happening in the channel is even more new, and that is they're not bouncing down to the conduction band. You don't have that type of scattering. If they're going to scatter, they're going to go all the way back. They're 1D. They can only go one direction or the other, and it's most likely going to happen at one of the contacts, where we have a certain transmission of getting the carriers from that semiconducting channel into the contacts. So in an equation sense, this is how these two things would compare. This is a standard kind of an on-state MOSFET equation. I have things like carrier mobility, spatial dependence, charge that's in the channel, and a certain bias I'm applying. For nanotubes, and I know it may look a little less friendly, but it's not too bad. But look at some of the differences. There is sort of a charge in the channel effect, but it's based upon the density of states. I have this sort of bias dependence, but it's based upon where my Fermi levels are aligning at the source and drain. And I have this carrier Fermi velocity and transmission at the contacts. Over here, no density of states consideration, no consideration of the contacts. And over here, no spatial dependence. This is like a single molecule conducting, and no mobility dependence. Because what's happening in the channel at any respectable lengths that I would be interested in this thing is going to be ballistic. So it's really about getting the carriers in and out, and not what they do when they're in there. So there's a bit of the difference. Okay, so a couple motivations for why we're pursuing this, and then cover of these challenges. Here's another way to look at Moore's Law. Another, in my opinion, more correct way to look at Moore's Law. This is just a fun way of seeing what's happening over the years with how we change devices in order to keep scaling them. But over here is where I want you to pay attention on the right side. This is the plot of gate length. So you always see minimum feature size, and most people, even technology people, have no idea what it is. What's which feature? But it's obviously something important that gets very small. But it's not the channel, it's not the gate, it's something else. So when you look at the gate length, which is very critical because when you shrink down the gate length in a semiconducting device, the transistor, you lose control to other sources like what voltage you're putting over on the drain. So making the gate small can be challenging. And you can see there were several generations in the mid-2000s where we really stalled gate length scaling. Even though we delivered from one node, which would have been probably the 45-ish, I'm guessing, or maybe even before that, we were able to deliver a new technology with more transistors. We couldn't make the gate length smaller because the negative effects were too great. And that's a big deal. Now, there was, with the 22 nanometer, Intel was able to finally give a new gate length scaling with the FinFET device. But even then, there's some unknowns about what we're going to be able to do stepping forward. So this is a really important thing to consider when you're thinking about something to replace silicon or give you a better channel, more ideal channel. What can you do with gate length scaling? Because if you can only give us one little node, is it really worth it? Is it going to be able to scale further, and how far can it go? So with nanotubes, this is a question that was only asked kind of recently because for years, people thought, well, they're so small, of course we can make tiny channels out of them and they'll be perfect, they'll be terrific. But the theoretical evidence was contrary to that. The few papers showed that you had negative effects like source-drain tunneling because of the very small effective mass, that we're going to degrade what happens at small channel lengths. So we did some experimental work, which I won't go through the experimental details for sake of time, but here is some images of the device. We specifically were looking, this is one of those papers where we really did just want one or two devices. We wanted to know, can it work? That was the question. Can we make this experimentally and make it work? And making a channel that's sub 10 nanometers is not straightforward. There is no lithography process in place that can give you a liftoff of two metal contacts with a sub 10 nanometer spacing. So we had to do some creative work to obtain that. And here's the result. So I'm not going to go through all the little details of how these devices look here, but if you look at the left, this gives you the scaling trend on the same nanotube of 4 different channel lengths. And you can see the improvement in what's happening with the current in the on state, with some clipping of the minimum current in the off state, but the subthreshold slope, meaning how the device switches or how really, if you look at the power of a device, how low of a voltage you can use, the subthreshold slope is one of the most important things, and that remains relatively consistent, which was an important observation. But what should matter to you, especially if you're not a double E and can't look at this and get some valuable information, is what does this mean with respect to the other options? And so compared to silicon devices specifically, we scoured the literature and found the 3 best performing sub 10 nanometer channel length silicon devices. And you may look at this and think, oh, sure, best, he chose a decade-old data just so that it would look good. No, these really are the best. Now, someone may have tucked on their shelf at Intel or maybe even an IBM that I don't know, some device that's better, that they've built, that they've experimentally tested at sub 10 nanometers, but it's not in the literature, not when we looked this up. And so these really are the best ones that were there. And some of them are not even ideal in terms of what you can get with dimensions. This nanowire is 13 nanometers. They can make them comfortably to 5 nanometers now, which should be better. But this is what you have for the comparison. Nanowires, fins, and ETSOI, which is a very thin layer of silicon used to help reduce that body thickness. And the other question is not just finding which ones to compare to, but how to compare them. Because this is not apples to apples. I can't just choose something and say, oh, well, look, of course a nanotube is better. So we decided, well, if these things are ever going to be used for sub 10 nanometers, they're going to have to run at about a half a volt or probably less than that. So if we choose a specific operating voltage and assume the same threshold voltage for the devices, then I can look at the current at that operating voltage for all of the devices and get a somewhat realistic comparison between them all. This is showing their subthreshold swing. That's another discussion. The nanotube is in blue and has a scaling trend similar to the other guys, though I will say it has a lot of non-idealities in the dielectric that should shift the whole curve down a bit more. But it looks good, just comparison for face value. Now this is looking at that current based upon diameter normalization. But as much as I like that result and would have been thrilled to just publish that as is because it makes nanotubes look just heroin. They are so great, right? Their effort, they can provide so much more than anything else in current based upon the same operating voltage. But this is completely unfair because a nanotube is only 1 nanometer. So the diameter normalized current is going to be extremely high, and I'm never going to make them exactly next to each other for several reasons. So it's more fair to look at a pitch normalized current. And these nanowire guys were just as bad, by the way. They reported diameter normalized in their paper, so shame on them. Because you're never going to put silicon nanowires right next to each other. You have to get a gate in there, right? So we modified this for a pitch normalized. If you had nanotubes at an aggressive 5 nanometer pitch, nanowires and fins at a mostly unrealistic 20 nanometer pitch, because you still have to fit all of their gate stacks, whereas the nanotube works just as well in terms of the gating with a single gate below it. So I'm not limited by the gate stack fitting in. And this is where it looks with pitch normalized current. The nanotube is still more than double what you can get out of the nanowires. So it's still great, but it's also a bit more realistic for what I could expect at a low operating voltage from the nanotubes. And it's promising. Okay, so the challenges. So all of these are great things, and everyone obviously should be coming back to this, but what the challenges, the main challenges are important to know because these are the things people remember when they think about why we may not see as much from nanotubes at the moment. The first one is separating semiconducting tubes. Carbon nanotubes can be metallic or semiconducting, the single wall type, based upon their chirality or their diameter in the simplest term. So what do you do to isolate nothing but semiconducting? Well, first, if you look at what is needed, if I have a chip with, just as a back of the envelope, 1 billion transistors and 3 nanotubes per device, because you're going to need more than one of those in each device to get enough current out of it to drive things on the chip, then that's about 3 billion CNTs on the chip, which means I need a purity of about 6 nines, percent semiconducting nanotubes out of this. That's pretty daunting. Right? And if you want to put that into perspective, this is where we are now, or close to now. I have a more updated version of this, but if you look at trends in what we can do to isolate semiconductor nanotubes in a solution process versus isolating them at growth, which two important and hopefully eventually will work together approaches, this is what you see. Now, this looks like we've made it, right? But I'll show you what this purity is right there. This is the work from Mark Hersham's group at Northwestern from 2006 that they developed into this company. You can now buy a little bottle that is 99% pure semiconductor nanotubes. So that's excellent. That's amazing progress. But the problem with it is that, I guess I have it on the slide after this. Oh, no, here it is. This is the problem. The way that they determine that is using something like this UV vis spectrum. And you tell me if you can tell how high that peak is down here in the red. Can you see how high that guy is? I don't know. I mean, you say, oh, give me the numbers and maybe I can tell. Good luck. It's not easy to tell. And that's why 99% is the best we can tell you from UV vis. It could be 99.99, but there's no way we can tell by how small this peak, which shows up when a metallic nanotubes are present, how high that is compared to the semiconducting. So we have a characterization issue. We have an inability to determine how pure these solutions really are. And it's nice that we can get to the point where we say 99%, but we have to have the ability to say a lot more than that. So this is one of the techniques that we've been using most recently at IBM, and a lot of other groups have worked on this. It's a chromatography setup that allows the tubes to have different densities going through this column based upon their metallicity. And that's just a matter of how they bundle with different surfactants present. And that gives you a very high throughput technique that at the UV vis side gives us as good of material as the stuff that does not give high yield. So that was an important thing for us. But as I said, most important was determining what the actual purity is. And this is not a final slam dunk solution. It just gives us to really one or two more nines. And that is make devices out of them. Actually, to build near 10,000 transistors and put them through a semi-automated probe station, let them run for a day or so, and then determine how many of them were metallic. And based upon that, give ourselves a more comfortable figure. And in this case, the best we have that I'm showing on this slide is 99.9%. And that's good that we can give some real data towards that, but we're never going to build enough devices and have enough hours to test something that gets down to the 5 or 6 9 range. So this is a real big materials issue that we've actually started a new collaboration with the folks at NIST, because this is what they do. This is material measurement and characterization, to try to figure something else out that can give high throughput, better accuracy on knowing what type of purity is present with nanotube solutions. Okay, so that's one of the materials issues. The other way is the ability to put the nanotubes where you want them and do that at a pitch that is at least 10 nanometers or lower. And that way you have enough of a current per width of a transistor device and are able to rely upon exactly how many channels you would have based upon where you build the device on a substrate. So that's a daunting target when it comes to nanotubes, and I'll show you why on the next slide. Nanotubes are not rigid structures when they, at least not in most of the ways that they are placed on a substrate. And I have a comparison down here. I like to think of them as sort of al dente pasta noodles. If you just spin them out on a substrate from a solution, they're most likely going to look something like this guy, wrapped around there instead of nice and rigid like something that is not hollow, like a nanowire would be. So this is something that has to be dealt with not only from controlling the orientation of the material, but also keeping it from interacting with its neighbors. There's a interaction, the van der Waals force, that lets the nanotubes join together with, depending on what solution they're dispersed in, unless you put something on them to specifically keep them from doing that. So those are the two biggest issues with respect to controlling the material when you want to position it on a substrate. So I'll highlight one of our approaches. There's actually a few good papers that have come out in the last year or so that have unique approaches for solving this problem, or at least on the path towards solving it. This is the one that we've done a lot of development at IBM. Really over the years, there's been good work there on it. And that is using some type of functionalization, either of the nanotubes or of the substrate or of both, in order to attract them selectively to different surfaces. In this case, using an NMPI molecule that selectively attaches to a high K dielectric like hafnium oxide and will not attach to SiO2. And then having the nanotubes wrapped with one of the more common surfactants, SDS, which provides sort of a positive charge end where the NMPI has a negative charge end. So you have a coulombic bonding that takes place, putting the nanotubes on those surfaces. The selectivity on this actually is near perfect. It is one of the things that's not a problem with this approach. The nanotubes will just stick where that hafnium oxide is and in the NMPI and not on the SiO2. The hard part about it that is still being worked on, and I have two SEMs showing parts of this. This one has some lines added to show you where the tubes are, but that is getting them to be placed close enough together. The smallest that we have in this work is about 100 nanometer pitch that is a really reliable approach, so 10 nanotubes per micron, about an order of magnitude away from where it needs to be, because you start having issues with nanotubes jumping across the trenches. But this is one with 70 nanometer trenches at a 200 nanometer pitch. And you can see the tubes like to align up within these trenches fairly well. And if you restrict them in the other dimension, then you can start to make devices at a large scale. And this is the sort of platform we use for testing those 6,000 devices for looking at the purity of the solutions, so that we can nominally make sure we have one nanotube. And that's a whole discussion about whether we know if there's one or more than one. And if you're curious, you're welcome to ask about that. Okay, so those are the two materials one. Those are the ones that most people know about because they know they're hard. But there's nothing fundamental that suggests they're impossible. They just are hard and caused some of the people to get out of the minivan on our little road trip analogy. The device challenges are also important, and I have 4 here, but they move rather quickly, and they're the ones that I think are the primary bottlenecks when you're looking at it from a double E standpoint. One of them is the variability. I want to give you an experimental idea of why this is so bad, and this is shown somewhat here and on the next slide. Variability, what I mean is if you're building devices out of carbon nanotubes, and you have a band gap that's pretty consistent. Let's say you have the diameters that are close to each other. So your band gap's not changing a lot. What would the device characteristics look like? Well, this is only 56 of them on a chip. And you can see, and this is over a 4 volt range, there's a spread of over a volt in the threshold voltage for these devices. Just having the same gate dielectric, the same device structure on the same chip, that's a lot of variation. The other thing that varies is the on state. Even if these shifted together, there would still be variation. And the hysteresis. The fact that sweeping these devices in different directions shifts the curve or the threshold voltage, which is problematic when I want these things to work in a digital logic application. Over here is a sort of a schematic picture looking at why this is the case. Nanotubes are these tiny single molecules. So with all that's happening on their surface, nothing is protected. And because of that, they have a lot of sensitivity to what's going on around them. And that makes them great for sensors. They'll pretty much change their conductance in the presence of almost anything. But it makes a problem when I have a transistor that needs to stay the same and be the same as its neighbors. So there's a hydroxylated charge, ended surface, which is on most of these oxides, different traps and charges that are likely part of the dielectric structure, and all of these are going to have some contribution. So one of the things that we did to try to figure out what the main source of this variation is we built a lot of devices along the same nanotubes. This is a long nanotube, and this is about 10 devices, and looked at the IV curves. Because we figured, well, if at least we can make sure the diameter is the same and the devices are identical, then we can get a feel for what's being caused by the surroundings. And this is how the curves look. This is from a solution nanotube with 4 devices, and this is from a long CVD nanotube with 8 to 10. And the variation is high, but we wanted to see how much of that is due to the surface and how much of it is due to the gate dielectric, how many charges and impurities that are present there. So we did a pretty crude passivation layer, and I have another one I'll show that's better, but this is just an HMDS layer, but deposited in a dry vacuum environment where you have some elevated temperature to help drive off the adsorbates, and then the HMDS serving as a protection from keeping the adsorbates from coming back when I put my sample back into the air. And what was amazing is putting this sort of a crude layer down did a miraculous job of pushing these curves together. They're still not perfect, but just by passivating, these same devices before and after tighten considerably. This tells us that a lot of that variation that's present is caused by the interaction between the nanotube and all the stuff that's happening on the surface around it. So protecting them in the proper way is a very important step to having the path towards getting a transistor that makes technological sense. So where are we now? This is some very new data that uses more robust layers that were ALD oxide deposited. And if you're curious about these layers, I'm happy to talk about them at greater length offline. I'll talk about this one again in a moment. But the hysteresis suppression is really, it's near perfect. The devices, if they have hysteresis, is very small in any of the ones with this passivation technique. And the threshold voltage distribution is tightened very well. The red is before and the blue is after. One thing to keep in mind here is that we're still dealing with non-optimized dielectrics. There's no engineers have taken this challenge like they have with silicon and said, we need to make this perfect, this dielectric. We need to get the anneal conditions down and all the other important parameters. So we're still using stuff that's sort of off the shelf, and that could be what's remaining in terms of this variation. Okay, NFET. So that's variation. There's 3 others really quick, and then I'll summarize this for you. It's a lot easier to make a PFET from carbon nanotubes. It is a mistake that people say carbon nanotubes are naturally p-type, because they are not. They are intrinsic semiconductors. They have no natural doping or charge present. You have to put that in to the nanotube. And so the way you put it in determines the polarity. And getting a high work function metal like palladium or gold is a lot more straightforward than a low work function metal like erbium that oxidizes very readily. So that's why most of them, almost all of them, have been PFETs. Okay, and in this case, it shows the band diagram. Look at that, very simple picture of injecting with a high work function metal into the valence band with holes. So what I want to get to is a metal that can be as robust and compatible with processing to yield InFETs as opposed to the PFETs. One thing to keep in mind here at the physics transport level that a nanotube is very friendly about is the fact that the effective mass for the carriers is identical between the electron and holes. There's symmetry in the dispersion relation. So this is great news for me. If I could just get them in there in the same way or similar way to the holes, then I can have electron transporting devices that are very complementary. So where we are, well, there's been some good progress made in the years. It started with kind of some one-off demonstrations where people would do some type of a dopant, not substitutional or interstitial the way that you may think about it with silicon, but a dopant where when put in the vicinity of a nanotube creates a charge fluctuation or a permanent sort of charge shift, like an electrostatic movement of the band structure, and that way effectively dopes the nanotube. These are some examples of that. There's problems with this type of a chemical doping. One is in terms of reproducibility, consistency across the substrate, and robustness to air, especially these earlier ones where they use potassium. The devices turned out well, but these sort of things have issues in the manufacturing sense. So what's happened most recently is people have looked at low work function metals, which creates the picture that I show in the bottom right here, sort of the inverse of the PFET. But the poor air stability, if you've ever worked with these materials, if you have them in an evaporator and you have them exposed to air and you come back a few days later, you'll probably have a little crucible of powder left in there. These are very temperamental metals. And so you have to be careful about how to use them and how to make sure that your yield can be consistent because they're going to oxidize. And some people have shown good work on this. Mostly Lin Maopeng's group from Peking University in China have done great work on scandium and yttrium. But there's still this yield question of getting it to the place where it's comparable with what you get from palladium and the PFETs. So this is some results that we did and we've modified recently. So I'll skip to this next slide to show some of the slightly newer data. This is using erbium. It hadn't been explored before, and one, we just wanted to be a little different, and two, it worked better than yttrium for us, so we decided to stick with it. But we wanted to look at this from a more technology perspective, and that is getting the yield higher. Not just getting a few really good devices, which we did, but looking at yield. You could see at the erbium devices here, the InFETs, the variation is a whole another topic, which we have some interesting insight into now, but it's a lot bigger than it is for the palladium devices. But the performance and the yield on a chip, when you spread the same density of nanotubes out and create the random devices, the yield for erbium contacted ones was very comparable. And this plot, it looks a little confusing. All you're looking at is current at the bottom, the on current, and the count, number of transistors with that current. So based upon the area under the curve, you can see the yield comparisons. And the erbium is very similar to the palladium. This one's lanthanum and yttrium down there. And this told us that if we cap this material most appropriately and passivate it immediately after deposition, then we could start to look at devices that approach the yield of what we can get off of these non-oxidizing high work function metals. Contact scaling. This is one that's near and dear to me because it's one that we looked at when I came to IBM early on. A lot for years, and I talked about this earlier in the talk, we only looked at the channel, which would be under the gates right here, the gray areas. This may be a confusing picture to you. You should look up here at the top. The channel is the area between the metal contact bars up here. The contact is the length over which the metal covers the nanotube. For years, we never even paid attention to this. And I think the motivation was that the biggest problem with silicon was short channel effects from making the channel small. So what should we fix? Well, it's making better devices with short channels. But all along the way is in the back of the minds of the technology people, but we have to make small contacts too. And there were some people who actually felt that based upon some proper motivation, that small contacts may even be better for nanotubes because you enhance the field there, they're Schottky barrier controlled, so maybe injection improves. And so we looked at it experimentally to get a feel for how good or bad the situation is, built a set of devices along the same nanotubes, and scaled the contact length. So the channel length remains about the same. And this is the result, the most important one in the bottom middle here, which plots contact resistance versus contact length. And you can see at below 100 nanometers, you see a dramatic increase, about a 1/LC relation in that contact resistance. And this is not to say, oh, well, great, a hidden huge problem with nanotubes. It's never going to make them work. Whether it ever keeps them from working or not is an unknown, but it's not unique to nanotubes. Any type of transistor, including the standard MOSFETs throughout the ages, have the same type of a trend. In fact, it has a similar 1/LC dependence. But the physics are entirely different. What I get out of a 3D to 3D silicide type of a contact in a MOSFET is very different from a 3D to 1D contact to a little carbon nanotube, where you have Schottky barrier and other issues that are likely playing a role. So there's so much work that could still be done to understand this, and hopefully, by understanding it, provide some improvement for this scaling trend. One of the things that we've done most recently, I'm missing actually, we have a couple more curves on here that are interesting, but we're looking at how different contact metals scale compared to palladium. So the orange scaling trend is the one that I showed on the previous slide. Our other work we've been doing now is looking at different metals and different interfacial layers and how it affects what the scaling behavior looks like. Because what I want more than anything is to get some devices down here in the lower resistance and small contact length area. And that requires changing this type of scaling behavior. So there's a lot of work that remains to be done in this particular area, where a lot of material science, good work with interfaces could play a big role. Okay, finally, this is where I'll wrap up on my experimental details and then summarize the talk. I've got fun animations there, but the idea is when I'm building a transistor for technology, I have to end up with a gate that is self-aligned. And I also started the talk telling you what the ideal transistor is, and that it should have a gate-all-around channel. And those two things come together in this recent work that we did. And this is the process flow for it. So it's so new, I actually show some of the experimental details here instead of skipping over it. One of the hard things with nanotubes is you can't put them in a reactive ion environment, really virtually any, or they will etch. They're very reactive, being all on their surface and having their bonds sort of stretched tight with rolling them into the cylinders. They are reactive to virtually any species. So if I want to etch something anisotropic, it becomes a real challenge. So what we did is we decided we want to suspend the channel and we want it anisotropic, but we can't do the dry environment etch. So we used an SOI wafer and made use of the crystal orientation of the silicon, where when you etch it in a wet environment, it will actually etch anisotropically. And the etch that we used was a KOH etch, which we tested the tubes and they survived just fine without degradation. And it enables me to suspend the nanotubes across this channel area where I put the source and drain down first, and they mask it off. And you can see these SEMs show it really well, where the nanotube is sitting on the SiO2, it is charging, so it's glowing, and then it lifts up, goes across the channel, and goes back down. So they're nice, suspended across the middle area, and this is following an ALD, which in our case, we use this adhesion layer, which is a modification of a layer that was used actually by IBM colleagues that are now here when they did the first gate-all-around device, and they used this sort of NO2 functional layer. We modified this to keep it from degrading the transport properties and from contributing to traps and other issues in the dielectric stack. And you can see how the nanotubes coat nicely when they're lifted up off the substrate in this gate-all-around fashion. Yeah? The self-alignment, I'm not going to get into in great depth. What we've done most recently is more exciting than what I have here, so I'll tell you what it is. And that is, we designed this structure so that what you do is backfill the whole thing with something like tungsten, where we would sputter it on and it would cover everywhere and fill these little trenches, and then polish down the tungsten in a CMP process. And we've now done this on our 200 millimeter wafer fab that we have at our facility in Yorktown Heights. and shown a selectivity between the tungsten and palladium where it gives a nice polished surface like this. This one is actually from a liftoff little trick that keeps the gate self-aligned to the contacts, but it has a much better manufacturable tie. Okay, and this is the pretty TEM image of that device showing the uniformity of the gate all around. So the nanotube is right in the center there, and then you have this adhesion layer of about a nanometer or less, and followed by the gate stack, and then eventually a tantalum nitride gate metal so that it also encompasses the channel. This is just looking at that TEM at an array where you can see the uniformity on the different nanotubes. And here's the device results. Another thing I don't have a lot of time for, but anyone who knows the field would be curious why this thing is an INFET, because it has palladium contacts, and yet it's a really true INFET. And there are really good explanations for this now after we've done some further device work on it. But it does look like a good device from the general perspective in terms of on current and switching behavior, with the need for improvements in the dielectric still, because we're just using an as-deposited ALD film. There's no annealing to eliminate the charge issues in the dielectric. So based upon those non-idealities, it performs very well. This is a comment that I like to make sure and make, and that is regarding why gate-all-around, because it's easy for me to tell you, as I did for many years. This is actually a plot from a paper that worked on with Tim Fisher here, that I like the paper because we were working a lot on these gate-all-around, surround gate, and back then I motivated it almost predominantly for the electrostatics, because it's the best electrostatics. But the fact is, it's not entirely fair for nanotubes. They are only 1 nanometer. Making a single gate below it is plenty of amazing electrostatics for making a sub-10 nanometer channel. And we showed that with the sub-10 nanometer device we made with a cylinder on plate type of a gate geometry. So gate-all-around is not so much needed for the electrostatics from nanotubes, it is that you get an isolation from those stray charges that I talked about with respect to variability. It gives me the chance to control exactly what's encapsulating each of the channels and even cap them with their own metal or conductive gate so that they're not interfacing with each other. Okay. So let me sum this up. This is another discussion from that I won't take the time to get into because I want to wrap up here. This is now my 2 cents from me personally. When people ask me all the time, since here I am still working on nanotubes predominantly, why do I still work on them, and do I think they'll ever actually reach a technology? Well, my answer is twofold. One, what do you mean by a technology? Because when I look at the next generation of electronics, I don't necessarily see Moore's Law anymore, as I told you in the beginning of the talk. I see bizarre stuff like this, right? People want their phones to be flexible and their windows to turn into electronics and all of these crazy application-oriented things, not performance-oriented. We're sort of making a shift there. And in that space, nanotubes do an amazing, unique job enabling devices that could feed that type of a new field. So that's the thin film devices, mostly TFTs, that would be applicable there, but there's no reason why in the long run they can't have a need for more high performance stuff. So my summary of this, I like putting it this way. This is my answer to should you replace silicon with nanotubes, and why or why not? And I relate it to my kitchen remodel, so I'll show you why. Here's my kitchen. This is my kitchen, circa 3 years ago. It's a nice kitchen. It's somewhat inviting, and it worked. We were able to cook food in there that was edible, and everything seemed to be perfectly fine with the kitchen, except that the user didn't like it, mainly my wife. It was, it was a subpar kitchen. It was old, outdated, not flashy. People didn't come over and we said, have you seen the kitchen? Right? It was not a big deal to us. It was just a kitchen. So it wasn't getting any better. So we wanted to change it. So change, we found out, requires a lot of hard work. It requires a lot of money and a lot of time and more money, right? And eventually you get a new kitchen. And you know what's great? It makes the user very happy. And it still works. It still makes food just fine. Very flashy. People come over and are like, you've got to see the kitchen, right? Because we're proud of this change. We think it cost us so much that we're proud of it. But it cost a lot of money. And it will not last forever. So when I think about this question, well, will nanotubes replace silicon in high performance space? I think the answer is, how much do you expect to get out of it, and is it worth the cost? For our kitchen, I think it's been worth it. But when you talk about making the paradigm shift that it would take in a technology sense from what we know in silicon to something that has a lot of unknown still in nanotubes, I don't know the answer to that yet. And that's why I think more people should still be concerned with how to fix the problems with nanotubes to come up with that answer. So maybe it's more like remodeling a basement, where you don't have to mess with the kitchen. You can just do something in a space that is not currently existing and remodel it, provide some new functionality that nanotubes uniquely enable and not disrupt what people are afraid of with respect to change. So this is a plot. This will come out in about 2 days. I wrote this little viewpoint here that talks about nanotubes. I've tried to scream really loudly to get people's attention about why they should still be considering nanotubes, and I think this may get some people's attention at least. It's just a little blurb where I show this plot about whether or not we can ever reach what we need from nanotube technology. And one of the things that I think is the biggest misconception is people say, oh, well, you'll never get to the type of low metallic nanotube percentage or high purity semiconducting, which is the target here. Or, oh, you'll never get them to place at the density that you need them to place. And I hear this everywhere. And so I said, okay, well, let's believe in scientific trends and plot data points that are real based upon the literature for both how I place the nanotubes at a certain pitch and how pure they are, and decide whether or not we feel the trajectory suggests the ability for a solution. And that's what I show here. Whether or not this will happen is a complete unknown to me. And the fact that it will get harder as you get closer is not an unknown to me. The problem is people don't realize that it did not flatten out yet. And they have to come to realize when they look at what they spend their time and money investing into, what is the end product? And I contend that nanotubes still offer something better than virtually any of the other competition. The problem is that so many people have gotten out of the minivan and need to get back in and put more work into getting to the goal, or at least figuring out why we will never get there. All right? So this is a summary that shows all those challenges I highlighted for you with some of those promises that I spent time on in the beginning of the talk. And thank you for listening to me go over a lot of information. And I also acknowledge the many collaborators that we have at IBM right now working on this. Thank you. Happy to answer any questions. Shahan?
Thanks for the passionate talk on TEM. I'm glad so much more passionate on that. So in the slide that you showed the sub-10 nanometer FET, you compared the characteristics between different channel lengths. Are these all made on the same nanotube?
Oh, yes, it was. All in the same nanotube.
And you said the short channel effect is really minimal, but I saw the offstate actually increased with the channel length decreasing. So what is the reason?
It's a great question. Honestly, we attribute it to the carriers injecting over the other end. When you're switching it at that bias, which we were, I think, a half a volt on those curves, and are pushing the bands low enough towards the off state that we start to get electron injection over the other side. Well, why does that become more prominent at the smaller channel lengths? Well, there's a lot of discussion about that, but a lot of people want to attribute it to source drain tunneling, and we see no evidence of it being source drain tunneling with devices. And those are the two things we can come up with that would cause a clipping of that minimum. Yes?
You got a lot of the individual nanotubes, so if you scale up in the industry or the technology, so how precisely you can put the nanotube into the circuit?
Put them on the substrate when you need them, the placement?
Yes.
Well, I showed some of the work that we've done with the functionalization of the surface and nanotube for placement. There are other people who work on trying to grow the nanotubes into nice aligned arrays, which is excellent work, But what has to be considered in whatever process is used is not only the end goal of getting them at a sub 10 nanometer pitch, but also making sure that what you use to place them is compatible with what you use to purify them. And that's why the work that we're doing with the functionalization is a solution process approach, simply because it gives you the most pure nanotubes. So we can start with high purity semiconducting and use a chemical process to place them into little trenches and be able to maintain that purification level. Does that make sense? So there's a lot of approaches out there is the real answer to getting them where you want them. Nothing has gotten better than about 10 per micron so far in a controlled pitch. Yeah.
You mentioned that about 10 years ago there was a strategic shift because of thermal concerns. Have you looked at the factors for nanotubes versus other alternate future technologies in a thermal sense? And in particular, I'm interested in whether this ballistic type of transport has any advantages or disadvantages thermally.
It's a terrific question that someone co-advised by a mechanical engineer should have an easy answer for, and I don't. I know there's been work on it. I know there has, but, and you probably know even better than me. So I don't know how that picture compares to the competition. I don't know when you look at the scaled devices and here these are reliably ballistic, where I'm dropping all of that voltage at the contacts, and what does that do with my heat issues? I actually don't know the answer to that. It's a good question.
Can you comment why did you have this N-type behavior with palladium contacts?
Thank you for asking that. Yes. The reason is what we do with the dielectrics. So these devices have spacers, source drain extensions, spacers, we call it what you want, but little areas that are not gated by the electrostatic gate. And what happened is when we put this aluminum oxynitride, we called it, it really comes down to about aluminum oxide once it's annealed. It's an adhesion layer on the nanotubes to get the dielectric to stick. It's less than a nanometer. And then we put hafnium oxide on top of that. That creates this dipole at the interface between these two materials. Nanotubes are pretty sensitive, so it doesn't take a whole lot to cause a disruption enough to move the bands. And so that moves the bands enough to force injection, even though it's a huge shocky barrier, it's a thin barrier based upon the amount of doping, right, that moves those bands. So electrons are able to inject more readily than holes because we made almost come a thermal barrier to the holes, right? So the way we showed that is we took a device that was not gate all around. It was just sitting on a substrate, the nanotube was, put contacts on it, tested it with the back gate. It's a PFET. We knew it should be. And then we put those layers on top of it. Not as part of the gate stack, but just on top of the nanotube, and it turned to an NFET as well. So it pushed the bands down and once again had the injection of the electrons. So we were able to make PFETs with the gate all around simply by using an aluminum oxide gate dielectric instead of hafnium oxide. And now there's new issues. Now we have a spacer that is not doped, right? And there's a whole discussion about that. But it does still have a leaning towards hole injection based upon the contacts. Other questions, Mark?
I'm sorry, I missed most of your talk. It's really interesting. So a couple of questions. You mentioned briefly thin film.
Mm-hmm.
I know people have looked at carbon nanotubes as a thin film material.
Mm-hmm.
I suppose the considerations there are a bit different than the ones that you've been discussing.
Yes, they are.
I haven't followed that area for a while. Does that continue to be an attractive area?
Very attractive. And in fact, most of the funded work in academia for nanotube transistors is thin film devices. For flexible substrates or just thin films in general, that's where most of the work in the last year or two has really happened. We have some of our work focused there. Our end goal has to be high performance computing because we're IBM. But everything we do towards that end benefits what you do in the thin film space because the requirements are so much more lenient. You're typically dealing with non-ballistic, you're dealing with micron long channels or more. And we actually have a paper that'll come out in the next couple months that shows the low voltage potential. Now, low voltage is relative for TFTs. Most of them run at 3 volts or above on backplanes for displays. We show that, hey, you can make TFTs from nanotubes and have the same type of mobility of amorphous silicon, but run it at 1 volt. which, that kind of creates a new uniqueness of what you can do there. But, yeah, the requirements are much more lenient, and, I don't know, it's interesting. It's interesting in enabling a new space.
So on the high performance, you're talking about sub 10 nanometer, and I guess 10 nanometer silicon is under development right now. So the primary advantage would be power supply?
Primary, yes. Primary advantage, voltage scaling.
And what, you probably talked about it, sorry, but what kind of power supply are you looking for? 5 volts or less?
I mean, if you follow the trends, we should be at like 300 millivolts, right? By the time we hit 7 nanometers or so. I don't think anyone's going to give that.
Silicon will
Never get there. I think nanotubes will struggle under 400 millivolts, personally. I think they would. But I think they could deliver half a volt. And I think that is unique still. Experimentally unique. And with, obviously you could appreciate with your tremendous work throughout the years in the area that showing it experimentally is a very different thing from being able to show it in a projection. And nanotubes are still the only ones that you can experimentally show for sub 10 that it could work. And then we like that. Any other questions? Great questions.
Let's thank our
All right.